This video will cover the binary search. In this video, I'll cover what the binary search is, how efficient the binary search is, programming a binary search. For that, we're using a static data structure, one which doesn't grow and shrink, it stays fixed in size, a while loop, and some file handling. The file handling was in the last video, where we're building off the linear search to now look at binary search. Okay, so a binary search, how does it work? Let's just recall how a linear search works. So a linear search would go from the first item, if it didn't find what it was looking for, to the next one, to the next one, to the next one. And we saw that it wasn't very efficient because it could potentially be that it searches through everything in the data structure before finding it. And therefore, as the amount of items in our data structure increases, so does the amount of comparisons, so does the time it takes to do the search. So this time complexity increases. The binary search is a solution to that, something to try and reduce the amount of comparisons, therefore reducing the amount of time it spends. One thing that a binary search must have, however, it must have the data already in order. And that order can be ascending or descending, it doesn't really matter. Well, depending on how you go and code the binary search, that is, as long as it is in order. And in this example, we've gone for ascending because that's typically what we've got and what we deal with. So we've got some data, the 2, the 13, the 53, the 72, and the 134, and we've got what array positions they're in. So we've got 0 all the way up to 4. So we've got 5 items in this array. And what we do is we indicate what the smallest position is and what the largest position is, and then we look to find what the midpoint is. And the midpoint is going to be that index plus that index divided by 2. So 0 plus 4 divided by 2 gives us 2. So our midpoint is going to be here, pointing at the 53. In this little demo, what we'll do is search for a number that's not here. So we'll search for, let's go for 3. Let's go for the number 3. So we look at the middle of this list, and we're looking for the number 3. 53 is not 3. So what we do is let's just label these up. So that's the min pos, so the minimum position it could be in, and that's the maximum position it could be in. So min pos and max pos, and that's the mid position, the middle. And if it wasn't an odd number, it'd be as close as we can get to the middle. Looks at that, compares it to that. 53 is not equal to 3. Therefore, the number has to be at that side of our data structure. 3 isn't this, and everything to the right hand side is going to be higher. So we can immediately eliminate this side of our data structure. So to do that, we move our max position over to here. So the minimum position it could be is 0, the maximum position it could be 2, and we try and find the mid of that. So we have min pos plus max pos, so that's going to be 0 plus 1, which is 1, divided by 2, which would give us a half. But if we're storing it as an integer, it would just give us 0. So our midpoint would also be here as well. So we then look at that midpoint and say, are you the number we're looking for? If we're looking for 3, then it is not the number we're looking for. And it can discard everything to the left of the mid-pos. Now, just because this is the highest position, lowest position in the array, there's nothing to the left. But it doesn't necessarily mean that it would always be that case, but it would discard everything to that side, because every number to the left of 2 would be less than 2. So remember, we said that these have got to be in order, and we've gone for ascending order. And what that would mean is that we would move min pos to here. So the max and the min would be pointing at 1. And the 1 would do the same thing to calculate the midpoint. So the max plus the min divided by 2. So 1 plus 1 divided by 2 gives us 1. So we look, are we looking for 13? Well, we're looking for 3. So 3 is less than 13, so we're discarding everything to the right. So we'd move the max position to position 0. It starts to get a bit complex there, and I've not really given... Yeah, we've ended up with the max position pointing there and the min position pointing here. And when we've got the max greater than the min, that means that the data item we're looking for won't be there. And how many comparisons did that take us? Well, that was comparison number 1, that was comparison number 2, and that was comparison number 3. And that would be to determine that the data item we're looking for is not in this data structure. Now, for a linear search, it would have checked position 0, position 1, position 2, position 3, position 4. So it would have checked 5 times. So you see there's a slight reduction that has been. Now if we increased or doubled our size, so we now had 10 items, and again we search for something that wasn't there. Let's search for a larger number this time. Let's search for the number 4,000. Again, just to give us the worst case scenario that it's not there. Let's search for 4,000 this time, and it'll show us moving the pointers to the max and min number a little bit differently. So our min pos still starts at the beginning, and our max pos still starts at the end. And then we use our min and max. So we're storing the indexes in those. We use the min and max, we add them together, so 0 plus 9 is 9. Divided by 2 gives us 4.5. We round down because we're keeping these as integers, so it just ends up being 4. So that's the mid pos. So our mid pos is 4. Is the number at 4 equal to 4,000? No, it isn't. What is it in fact? Well, it's greater than that. So it must be to the right of this number. So we can discard everything to the left. and we move this min pos pointer to here, essentially discarding that side of the list, because it can't be in that side of the list. It's not possible for it to be in that side of the list. So our minimum position it can be is pointing to index 5. So again, we add, to find the midpoint between these two now, we add the min pos and max pos. So 5 plus 9, 14, divided by 2, 7. So our midpoint becomes position 7, our min pos. We see that this number isn't 4,000, and we look at this number in comparison to the number we're looking for. It is less than. So again, we know that it must be to the right hand side, because these are all still in numeric order, in ascending order. We can discard everything to the left. And our min pos, our min pos then is going to move to there, because it can't be anywhere to the left of that one, and it can't be that one. So we need to move it 1 plus the midpoint. And then we have 8 plus 9. $17, and then divide it by 2, is 8.5, which we then round down to just 8 because we're still storing things as integers. So our midpoint moves to there. So we've got our min point and our midpoint pointing to here, our max point to there, and we look, is that the number we're looking for? It isn't. So everything to the left of that point needs to be discarded. So our min point, min pos, is going to go 1 to the left of the midpoint, and it's going to point to the to the same place the max point pos is, which is 9. So we're going to have all 3 of our little pointers, midpoint, min point, and max point, all to the same location. Is that what we're looking for? No. Our number is less than that, so we're going to discard everything to the right. There is nothing to the right, of course, but if there was, we would be discarding everything to the right and moving max pos. So it must be to the left of here. The max pos moves to that left position. So the max position 8, the min position 9. When max position is, when min position is going to be, when the max position is no longer greater than the min position, it's not there. The item for our list is not there. The item that we're looking for is not there at all. And how long did this take to find that it wasn't in the list? Well, we had one search when the midpoint was there. We moved the midpoint here for 2 searches. The midpoint moved to here for 3, and 4 searches. So in the last example, we had 5 items. There were 5 items in our data structure, and it took 3 comparisons. This time we've got 10, so we doubled the amount of items. So the linear search would have been 5 on the first one, the worst case scenario of doing 5 comparisons, and it would be 10 on the second. But the binary search, because of the way it operates, the second, when we've doubled the list, it only increased its number of comparisons by 1. So doubling the list only increased its searches by 1. Because every single time we're going into the middle of the list and we can discard half the list. We can discard half every time. That's why we're calling it a binary search. We're kind of splitting the list into two, a list that we can discard, or a half the data structure we can discard and half the data structure that we need to search through next. And subsequently we can do half of that one and half of that one and half of that one until we either find what we're looking for or we can determine that it's not there. And here's another example. So I've got the list of ascending numbers here and the array positions 0 to 20. So sorry, I'll skip them over because I don't want 20, I want it to be 0 to 19. So I've got 20 items here, so again I've doubled what we had before in our last example. Last example we had 10 and it took us 4 searches to determine something wasn't there. In this example I'm going to choose a number that is somewhere in the middle. Let's go for in the middle of 8 and 13. So we're going to search for the number 9. So we're going to search for the number 9. And how the binary search works, it looks for the it looks at the min position, the max position, which is the start and end at the beginning, and then calculates the midpoint. So the 19 divided by 2, 9.5. So the midpoint would be here, location 9, position 9, and then says, is this the number we're looking for? So we can compare there. So this first bit here is one comparison, and we're going to be comparing this to the number we're looking for. We said we were looking for the number 9, so 89 is not 9. So what happens? It looks and says, well, what is it in relation to this number? So 89 is greater than the number we're looking for, so we can discard all this side of the list. We can say, you don't matter to us, you're not important. And our max position moves to 1 less than the midpoint. The min position stays where it is, because all we know is that the number is less than the one in the middle. So it could still be anything to the left hand side. We've got the min pos and the max pos. We add the two indexes, so 8 plus 0, and then divide by 2, give us the midpoint there. And then we know that 8 is what we're searching through next. So we're looking at position 8, and the number we're looking for is 9, we said earlier. And 9 is greater than the number we're currently looking at. So we can go ahead and discard all of those, the left hand side entirely. The max point pos is still going to remain where it was. We're not going to bother looking at any of these. And the min pos is going to move to 1 greater than the mid. And then we're going to try and find the midpoint again. And we're going to add the 5 and the 8 together. And then divide it by 2. and we end up with 6.5, and we'll be, because it's going to be an integer, it'll round down. So our midpoint is going to be there. So we're only going to be looking in the numbers in this range. I'm going to use this number to help us. This number is 21. What is this number in relation to what we're looking for? Well, this number is greater. So that means that we can discard all of that side now. Or we already discarded that part anyway. So it's just a case of discarding the rest of it, the position 6 to 9. And we're not actually deleting this stuff, we're just moving this max pointer or min pointer, depending on what's going on, to create as a little range that's going on. So our min pos is still in the same place. Our max pos has to go one less than the midpoint. So our min and max are at the same location. And then our midpoint is min plus max, 5 plus 5, divided by 2. So our midpoint is also looking at index 5. So we're looking at index 5, that's the number 13. The number we're looking for, 9, is less than that. So we move our max position pointer to one less than the midpoint. And because the max has become less than the min, we can then determine that the number we're looking for is not in these lists. If we were looking for 13, it would stop there and return 5 because we found it at location 5. At any point, if we've come across and done a comparison, say at this point we were looking for 8, that's it, we've found 8, we don't need to carry on moving the pointers. But this is the worst case scenario, that it's not here. In the worst case scenario, we end up with our max position being less than our min position, therefore it's not here. And our max amount of comparisons, well, we did a comparison here, 1, 2, 3, 4. So we had 4 when our list size was 10. Now we've gone up to 20. The maximum amount of searches we do is 5. So every single time we double the size of our input, we increase the amount of searches only by 1. So, how efficient is a binary search? Well, again, big O notation describing the behavior of a function, and we're looking for how it affects in time or space as the input size grows. So as the input size has grown, we've shown 3 examples now. We showed one with 5, we showed one with 10, and one with 20. As the input size doubles, the amount of searches, the amount of comparisons, only increases by 1. So we identify that as log to the base 2n. Log to the base 2n will give us the number of comparisons as the number of elements increases. Just like in the linear search, if we had 10 items, it would take 10 comparisons. If we do log to the base 2 of 10, I'll get the calculator over here. So log, where's my log gone? On your scientific calculators, you'll have it, or ln. ln, can we do it to a certain base? No, we might have to go to the web browser for this. got a web calculator form to do this for me. So log to the base 2 of 10 will give me 3.32. Now you must be thinking that's not 4, but that's telling us that it does 3 searches and potentially more. So we'd round that up. So 3.32 potential of it happening, searching for the item that we're looking for over 4 comparisons. So I know it's only 0.3, but we round up. Do this same thing. We'll look at log 5. Log to the base 2 of 5. Log to the base 2 of 5. It's 2.3. Again, we said it took us to find out that it was definitely not there. Took us 3 comparisons, rounding that up. And then log to the base 2 of 20. 4.3. So we said 5 comparisons maximum. So we see a definite advantage to using binary search over linear search as we increase the size of our input, as the input size increases. Just think about some larger numbers. If we're going from 1 million to 10 million, well, the linear search will do it over 10 million. But the binary search would, 1 million to 2 million would increase, the linear search would increase by another 1 million comparisons, whereas the binary search would only increase by 1. So efficiency matters, and it starts to matter a lot more when we have much larger input sets. So we need to get to programming the binary search. So we're going to use static data structure of an array. We're going to use the data structure that we had in the last video, the linear search. This time we're going to use a while loop because we're not definitely going through every item in the array like we are with the linear search. So we're going to use an indefinite loop. And we've got file handling, and we've still got the suggested text file, although you can go and find your own of 300,000 odd words. So onto the programming. So if you load your previous one up, we read all of the words into a text file. We've got a infinite loop that allows us to keep searching for the words, and currently we are timing the linear search, working out what position it's at, and then taking the time that it finished at so that we can output that. And we've got our linear search function. So we're going to have our binary search function. That's what we're going to make first. Static int. Again, we're going to have it return what position the word is that we're going to find. Binary search. So binary search, and again, it's going to take the same parameters. A string array. I'm going to call it words again, and I can do because this parameter is a local variable in this function. A string for the target. And then we're going to need a min position, max position, min pos, and the min pos will always start at 0 with our array. Our max pos is going to be equal to the length of the array minus 1. Minus 1 because our indexes in our array start at 0. So if our array was of size 10, the length would be 10, the maximum index would be 9. And then we're going to have our indefinite loop, our while loop. And it's while min pos is less than or equal to the max pos. Because we saw when the max became less than the min, or the min became greater than the max, however you want to refer to it, that's when we discovered that we hadn't found what we were looking for. At the start of every search, we had to find out what the midpoint was, so mid pos, and that was equal to the min position plus the max position divided by 2. Because it's stored as an integer, any fractional amounts that would appear from that sum would be just chopped off, truncated. So if we got 2.5, it would just give us 2. And then it's just a series of comparisons. So if the words at position at the midpoint is equal to what we're looking for, the target, then we found the word and we can return the position it's in. Return mid-pos. So if our middle position is the one we're looking for, the middle position has the word we're looking for, we return that mid position. Else, if the target is less than the words at that minimum position, at that mid position, then we need to discard the right hand side of the list. Of course, we can't do less than because this is strings. Compare to. So we're going to use a special string method for this, target.compareTo, and this, as you see here, it compares the instance with the specified object. So it compares the target with what you're going to put in the brackets and whether the instance precedes or follows in position. So compare to, comparing two strings like that. We use compare to help us with this, and compare to is going to return an integer, and if the target is less than the word it's comparing to here, it would return -1. If it was equal to it, it would return 0, and if it was greater than it, it would return 1. So we're going to look at it being less than, so less than 0. So if the target word is less than the word that we're currently looking at in the middle, that means that the target word must be on the left hand side of the list. So we need to move the max pos, and set it equal to the midpoint -1. And we want to set it to midpoint -1 because we've already discounted the midpoint or the mid-pos as being the word that we're looking for. So it's got to be 1 less than it. And then finally, else, it must be greater than. If it's not equal to and it's not less than, it must be greater than. If it's greater than, we need to move the min point equal to the midpoint +1. So we're discarding the left hand side of the list. And it will keep on doing that and keep on doing that until the min pos is no longer less than or equal to the max pos. And in the scenario where the min pos is not less than or equal to the max pos, that's where it's not in the array, so we need to return -1. So that's our binary search. A little bit more complicated to code than the linear search, but as we've seen with our examples, it will end up doing far less comparisons. Now, with the linear search, we knew how many comparisons it had done because we were able to see it. Well, we knew that it was checking everything up until the point where it found it or got to the end of the array. So whatever position it would return, it was that many. It was that many comparisons. Binary search, it's a bit more difficult to look at what's being compared. So just to help us visualize it a little bit, I'm also going to output what's being compared and what comparison number it is. So we've got something to compare it to. We've got the linear one to compare it to. So comparison number, and set it off as being one initially, and sorry, zero initially, and then when it gets to here, because there's that comparison, or the start of our selection statement, the comparison number is going to increment. We're going to have one comparison being made there, and output it so we get a nice output and see what's going on. Comparison number, and then we're going to concatenate our string, put in the comparison number, and I'm also I would like to know what word it's looking at. Word. Yeah, looking at word, and then going and concatenating the word that we're currently looking at, which would be words, and then at the midpoint. What comparison we're at, comparison number we're at, and what word we're looking at. So we should see that we're looking bang in the middle of our 300,000 odd words, and then it'll go to the left hand side or right hand side when looking for this. So we're just going to, for now, comment out the linear search because we don't want to try the linear search out, we want to try the binary search, passing in the words and the inputs. So passing in the full array of words and then what we wish to search for. It's compiled and running. Again, like the last video, waiting for the text file to be loaded. See the memory usage going up. Right. So the array is full of the words that we're looking for, and we want to search for the word duck. And we see there it took 15 comparisons till it found the word duck at position 93,737. Now the linear search would have taken 93,737 comparisons. This has just taken 16 because it actually did compare for the duck. And we don't like the idea that it took 16 milliseconds because we saw that we saw that the linear search didn't take that long, but the reason it's taken that long is because I've gone and outputted what's going on. So I'll take the outputs out in a moment, and we should see that come back down to 0. In fact, we should see that 0 or very close to 0 for any one we're looking for, even right at the end or something that doesn't exist. Let's look for a word that hopefully doesn't exist. Let's go for Dan frog. We're searching for a Dan frog. Or even easier, searching for duck, but with a capital D. Remember that the computer does perceive lowercase and uppercase letters as different numeric values, and we've not done anything to deal with that. Capital D there shouldn't exist. So, press enter. So it took its 18th one there. It took it 19 comparisons to not find duck. It did look at duck, of course, but it wasn't with a capital D. So if we try and just put a breakpoint in again to see how many things we've got in the array precisely, and we can put it into that calculator and see if what we got is correct. So in our array, we've got 370,104 different words. So if we put log to the base 2 of that number, we get, when we get past the adverts, we get 18.4, and as I've said, we need to round up there, so we did get 19. So the efficiency, the idea of using log to the base 2 n, whatever our number of elements is working here. It does follow. It does follow. It took 19 different searches or comparisons to decipher that the word wasn't there. And we could have estimated that. Okay, so one final thing, we need to ensure that it's actually not taking more time than the linear search, and what we'll do is get rid of or comment out what it's comparing to. And we should see that the binary search works very efficiently. Again, when we run the program, it's going to be the loading of the text file into our string array that takes a while. See on the diagnostic tools the amount of memory that we're using going up as we fill the array. And then it tells us enter what word we were after. So if we go for duck, again it took 13 milliseconds. There we go. So it must have been doing the CPU must have been busy with something at that point. But we're taking no milliseconds now. Even if we search for a word right at the end of the document we're looking at, let's open the document again. It takes a while because there's so many words. The zwitteronic, if we search for that word, still takes 0 milliseconds. And that's right at the end. If we doubled the size of this, if we doubled the size of our Word file here, our text file, and had 600,000 words, we would still only be increasing the amount of searches by 1. And again, we could have a look at that if we double this. So we need to double this number. So that number times by 2. Copy that. So it's actually 740,208. So previously we were looking at 19 different comparisons. Use this calculator again. And now we're looking at 20, rounding up from the 19. So this is massively more efficient than the linear search. Have a play around with it yourself.